Welcome to Brain Vision.
This is chapter 27, problem number 58. We're given a point charge that is positive, and we know that it has a velocity that is along z direction, positive z direction. So I'm writing the velocity vector as v times k hat, and the particle is experiencing a magnetic field, but we don't know the components of this magnetic field. Actually, that's what we're trying to calculate. The magnetic force acting on this particle is given to us as F naught being a positive constant times 3I hat plus 4J hat. Now, in part A, we're trying to determine the components of B sub x, B sub y, and B sub z. So in order to do that, we're going to go to the definition of the magnetic force for a point charge, Q, velocity vector, cross product, the magnetic field vector. So then Q, I hat, J hat, K hat, the x component of velocity, which is 0, y component of velocity, which is 0. We only have the z components, so I'm going to put B here. Bx, by, and bz. Now, this is going to be equal to q times I hat 0 times bz, which is 0, minus v times by, minus j hat 0 times bz, which is 0, minus v times bx, plus k hat 0 minus 0. So we don't have a z component here, as you can tell. Now, again, this is a force vector, right? Well, if I just redistribute this q, then we're going to have negative v by q I hat as the first term. The second term is going to be one negative here, one negative there. It's positive v bx q j hat for our force. We know that this should be equal to this force, right? F naught, then 3F naught I hat plus 4F naught J hat. Then the first term, the component of i's for each expression, they have to be equal to each other. So from here, we can say that negative V by Q equals 3F naught. If we were to isolate by, we would be dividing both sides by v times q. Then for by, what we have is negative 3F naught over qv. This is our y component of the magnetic field. Now let's move on with the x component. For the x component, then we have, y component. For the y component, we have 4F naught equals v bx times q. So I'm going to continue here. V bx q then equals 4F naught. Then if we divide both sides by qv, we have 4F naught over qv as our x component of the magnetic field vector. However, again, we couldn't say anything about the z component, right? Now, in part B, we are actually given the magnitude of the total field. So we are given B, total B, that will be equal to B sub x squared plus B sub y squared plus B sub z squared. So that actually, using this equation, we can get an information about B sub z. So if I basically square both sides, we have B squared equals B sub x squared, B sub y squared plus B sub z squared. Now, isolating B sub z squared from here, what we have is B squared minus B sub x squared minus B sub y squared. So B is given to us as 6F naught over QV. Then B squared is going to be 36F naught squared over Q squared B squared. 36 f naught squared over q squared and v squared minus, remember, b sub x was 4 f naught over q times v, then b sub x squared is going to be 16 f naught squared over q squared v squared. 16 f naught over q squared and v squared minus by squared. By was negative. We had calculated to be negative 3f naught over q times v. So when we take the square, negatives are going to cancel, right? 9f naught squared over q squared v squared. 9f naught squared over q squared v squared. Then for bz squared, we're going to have 36 minus 16, which is 20. 20 minus 9 is going to be 11 f naught squared over q squared v squared. So if we take the square root of both sides, then we're going to get the z component. Square root of 11 times f naught over q times v is the z component. Well, the positive or negative, right? Positive or negative.